Good afternoon, everybody. My name is Ryan Avery. I am the Wellington representative of the New Zealand Coastal Society, and I'll be your MC for this afternoon. We have got two great presentations coming, but first I'd like to give just a bit of a plug for the society itself, because we are a range of a wide range of coastal engineers, scientists. We also deal with managing and planning disciplines. We're also in a range of sectors, including consulting and government, research institutes and the education sectors. But ourselves, we are a subset of Engineering New Zealand, and our multidisciplinary nature allows us for bringing members together, making connections in not only engineering but all aspects of the built environment that has to do with the coastal side. There is no entry criteria for the society, so those of you who are not already members, please consider joining. It's only $85 a year if you are a single member, but there are also opportunities for students that are free, as well as corporate membership opportunities available. So yeah, check that out. That's a good one, and we can grow coastal society within Aotearoa. As far as our presentations, we're going to be kicking off with Richard Rynan-Hamel, who is a technical director for coastal engineering at Tonkin and Taylor. He is one of New Zealand's most experienced coastal engineers and coastal hazard specialist, as well as a long-standing member of the New Zealand Coastal Society. He has been involved in many of New Zealand projects from all the way back in the 1990s. So he's got some good experience. He'll be talking on natural and nature-based coastal design, as well as discussing the thought and design processes for the work he has undertaken. He'll also give a bit of an overview of the upcoming international guidance currently in preparation that he has been assisting with, as long as some resources and tools that have been developed as part of that. After that, we'll then move on to Curtis. He is from Engineering CFD. He is a consultant engineer with a mechanical background. He did a master's in computational fluid dynamics while he was in Ireland, but he then moved back in 2005 to set up his company, Engineering CFD. He is now working as the CFD consultant as part of that for a wide range of industries. And as part of that, he is looking at CFD simulation and possible applications within the coastal field, with an example of forces on a seawall. So yeah, we look forward to that. Afterwards, we will then go through all of the questions that you have put in the question box. So without further ado, I'd now like to pass on to Richard.
Hello everyone, thank you for that introduction. So my talk today is a bit of a quick romp through natural and nature-based coastal designs. Through the presentation I'll have some photographs and some projects that I'll sort of talk to as we move along. This is one of Tuamana Reserve in the Manukau, and I'll be talking about that as a specific case study, so we'll whip through that, and you've heard about who I am. So what we're going to be talking about today is what is natural and nature-based features, some of the key principles, and then some case studies, some challenges, and some resources. And it's not a new thing. Natural and nature-based features, I guess, had its gestation in the Western world sort of, back in the 1960s with the realization that we can't actually engineer everything, and the kind of forces that we're dealing with, particularly in the coast and fluvial systems, are just too big to be well engineered, and learning how to work with nature is much more sensible, cost effective, with more ecosystem benefit kind of approaches. So when we come with the definition, this is from the engineering with Nature Atlas, is natural and nature-based features, NNBF, or nature-based solutions, NBS, and sorry for the acronyms, I'm working with Americans, are landscape features that are used to provide engineering functions relevant to flood risk management and coastal management, where producing additional economic, environmental and or social benefits. And there's a wide range of NNBF kind of solutions, including beaches and dunes, vegetated environment, maritime forests, mangroves here in the sort of the central zones of the world, salt marshes, freshwater wetlands and fluvial floodplains, as well as seagrass, coral and oyster beds and barrier islands. And the big picture on the left is what's called the Delft Sand Motor. That was an experiment for a new maintenance strategy on the Dutch coast, looking to harness the powers of winds and waves and currents. And the idea of this was to help protect part of the Dutch coast while developing new beach and dunes, as well as protecting valuable flora and fauna associated with them. Now, the Dutch coast has been maintained through beach nourishment for a long time, since really the 50s and 60s, but this particular one was what's called a mega nourishment of 21.5 million cubic metres of sand deposited at one location, and then letting the winds and waves and currents move the sand along the coast, and that's been going on since 2011. There's lots of really good things on YouTube and lots of reports and evaluations. It wasn't without its controversy, particularly on the location where they got the 21.5 million cubic metres of sand in terms of habitat impacts, but through that process of taking a large volume of sand and monitoring, they also did refine large-scale dredging practices for winning of material, so there was a benefit and learning through that process. So the term NNBF has a lot of other kind of labels or similarities of approach that you might have heard of, things like working with nature, engineering with nature, the soft defences, green infrastructure, greening the coast, living shorelines, nature-based solutions, building with nature and ecological engineering. They all have reasonable similarities, and the common element along all these definitions is the focus on conserving, restoring and engineering natural systems for the benefit of people and the ecosystems we inhabit. And there's other related but not synonymous terms such as ecosystem-based approaches, natural infrastructure, green infrastructure and natural flood management. Now the image on the left was a nature-based solution we did in Tonkin Taylor in 2000s, I think, and this was a beach nourishment with two groins, as you can see on the top and the bottom of the screen, and these groins served two functions. One was to pipe stormwater out, and with the increasing development of this particular area, stormwater flows have increased, and that was causing erosion and assisting the longshore drift. So by piping those out through those structures, that helped preserve the beach, but also with the introduction of ferries in the Waitemata Straits, the longer period waves also reflected off the seawall that you can't see now, but is sort of sitting under the sand around that green perimeter, and that swell waves helped shape and control the beach shape. So that's understanding the physical systems and working with the existing environment to come up with a solution that is robust and works with nature. So when we talk about the key principles, it is using a systems approach, and this is leveraging what the existing components and attributes are, and other projects that may exist within that system. Part of the one of the key things with natural and nature-based systems is really understanding the scale. They're things that work on a system level, on a scale typically larger than, say, if you were doing a single seawall for a single property. That's not going to be, it'll be hard to do as a nature-based solution. If you're looking at within the whole bay or embayment or coastal cell, then something like a nature-based system could work. So it's understanding the conceptual system. So what is the context and the environment? What is going on? What are the things that are driving change within the physical system? What are the ecosystems and support within that particular cell? And then setting some clear objectives and goals and design principles and parameters all help inform a setup for an NNBF kind of project. The other thing that is important is engaging with the community stakeholders and partners to develop innovative solutions. And this is because there isn't one particular specialist group or interest group that's able to come up with a good solution. It's taking inputs from a wide range of stakeholders and interests and specialists to evaluate and test and develop a preferred option. And that means that by doing that, you end up with a sustainable or more sustainable and resilient solution with a focus on providing multiple benefits. With all natural systems, they do have natural variability and change. So you do need to have a look or anticipate that that kind of thing is going to happen, and then what is the management risk approach to dealing with how that system will adapt and change. So adaptive management really goes hand in hand with NNBF kind of principles, and that expecting change and managing appropriately is a necessary part of these kind of projects. So I talked about the requirement for a cross-discipline kind of approach, and these essential disciplines: engineering, coastal geomorphology, ecology, planning and governance. And when we think about the kind of application for adaptive management, we are, by understanding the physical system, the changes that we're both historic and present changes and future climate change influences, we can come up with possible actions to address and with trigger levels or responses for timing that match a certain response on that particular part of the project. Having those clear and measurable objectives can assist in identifying the project success and outcomes, and also managing expectations. With management and decision making that are flexible over time, that also allows that learning loop and the iteration. And through my experiences, you can model things as much as you like, but the natural systems always end up being more complex than our models can always predict. They provide useful indicators, but understanding that they're not always fully representative of the real world and things will change, the monitoring and adapting to what you see in the natural system is always important. And through those kind of processes, you can look at managing uncertainty over time, and that helps reduce risk and improve certainty, and both in terms of physical performance and cost. Through this process, there is a strong requirement to remain committed and engaged with your stakeholders, and they're part of the solution. If they're not, they can be part of the problem, so they can also help. They can help with monitoring, they can help with management, and through a good engaged community or stakeholders, they understand the objectives and parameters, and that helps with the reporting influence. Now there's a big project was carried out here. So on the right hand side there was a salt marsh development with a mud motor. So after the sand motor got carried out, the idea of using the same thing with mud was trialled in Holland as well, and this project focused on enhancing the salt marshes in the Wadden Sea, and the Wadden Sea sits behind the barrier islands and the levees and dikes along the main Dutch coast. And this was using dredge sediment from the port of Harlingen, and there was about 1.3 million cubic metres of mainly fine silts dredged from the harbour every year, and they were looking to beneficially reuse those silts to enhance the salt marsh in these Wadden Islands. And the additional benefit by placing it at this particular location, it reduced the likelihood of those sands and silts rapidly coming back into the harbour that previously occurred. Now, this project was carried out in 2018 and monitored for the last few years, and probably what was seen as an unsuccessful outcome. They couldn't see any net benefit, or the movements within the salt marsh were within the range of observed natural variability. So there's no clear outcome that the mud motor actually contributed significantly to what was happening naturally. And excuse me. So even unsuccessful projects, I guess, if you've got a clear objective and you've seen that they're not meeting what the modelling and the trends and the expectation are, at least allows a re-evaluation of the outcome, and for next steps or consideration of whether this is a useful outcome on a wider setting. All of those things are still very important. We're now going to bring some close to home projects. So this is Carnoustie Reserve in the Huri Inlet. This was one of the first projects when I came back to New Zealand in '94 that I got involved with. And this, for a local council, the objective was to build a seawall along a stretch of an eroding harbour edge. So in discussions with them, they also wanted to make sure that the seawall was cheap or low cost, because it was extending over quite a long area. And through the evaluation of the wave climate and the setting, it was clear that we were talking about something with a fairly low wave height, so 0.3 to half metre was the maximum wave height that could occur at this particular location. And the main issue was the geology was poor. Tauranga Group cliff coast or bank coast, and it was really the erodibility of the cliff rather than the power of the waves that was causing erosion. So we developed an alternative approach of a protective sill using basalt that with a small cut to fill from the foundations of the basalt created a slightly raised sill and an edge that dissipated some of the wave energies, allowing the rushes that existed in the more sheltered part of the bay to also extend along a more exposed part of the coast. So this has been in place for quite a while and proved to be a very cost-effective and increased biodiversity kind of setting for the coast, and it also allowed the banks to be vegetated rather than trimmed and placed with rock. This Point England Reserve was another local government project where there's an existing Reno wire-filled basket seawall running along a reserve that Reno was constructed in the 70s and 80s, and the cliff originally was an eroding cliff bank that had been graded back with the low wall. And the idea was to upgrade or replace the Reno mattress because they were corroding out and failing. Through the site investigation inspection, we noticed there was existing offshore reef, but a low reef along with a headland. Both of those, the reef and headland, have experienced some erosion. But by providing additional control by that reef headland, so by raising it and extending the influence of that reef, we created a space where coastal processes could support a beach nourishment, and a relatively small-scale beach nourishment provided protection to the backshore and also improved the amenity and functionality of that reserve and that grass space, allowing for more passive and active recreation. The only Onehunga foreshore was, or Tuamana Reserve, was a product of the motorway bisecting and separating the Onehunga township from the Manukau Harbour, and a commitment made by the roading authority at the time to restore the amenity of that. It took 40 or 50 years to do. But what we did at this project is develop a very good understanding of what the amenity or values from the community were, and then looked to try and replicate them using the natural systems and the waves and the currents. So we ended up with a headland controlled system of beaches, and the beaches range from cobbles to sand, with the cobble beaches and planting around the headlands creating a wilderness area sort of designated for wildlife and avifauna, and with the sand beaches more naturally attracted to residents and people using the parks and reserves. So using vegetation and morphology as a way of providing controls of where people like to go was a key theme from the landscape architects and the ecologists involved in the project. So that integration of engineering, landscape architecture, urban design and ecological output created a system that worked for nature as well as for the people, and ended up with nearly 7 hectares of new land and 3 beaches, 6 gravel beaches, and 1.3 kilometres of additional walking and cycleway, replacing a 700 metre long rock revetment. So natural and nature-based solutions sound good, but they are some real challenges in implementing them. So they require more adaptive management than traditional seawalls, and that requires clients to understand that change and the adaptation. We've had briefs where the beach nourishment requirements that have zero movement are guaranteed over 10 years, and we can't do that. We can guarantee it will move. There's also a need for space, both in the CMA and on land, and the current resource management process of avoiding effects within the coastal marine area can perversely support smaller footprint seawalls. But the use of NBF strongly aligns with Mana Whenua interests and New Zealand Coastal Society objectives. So in the introduction, it was noted that there is a guideline, and unfortunately it's almost ready. It should be out sometime in the next couple of months. It's 901 pages of guidelines and frameworks, so it is a comprehensive document, and I will share the link obviously with the Coastal Society when that comes available, but there's several other good links with engineering with nature and some performance metrics. Thank you. Sorry, that was a quick canter, but hopefully you found that useful.
Thank you, Richard. We would now like to hand over to Curtis. Take it away.
Okay. Very good. Okay, so it's slightly different take on things. Just focusing on CFD and where that could potentially add value to this kind of work. Ryan gave you a bit of an introduction, but yeah, so I started off at University of Canterbury in '94 in a mechanical degree, and then I sort of went off into the alumina industry and worked there for how many years? 10 years. And then part of that role, I sort of got into the CFD side of work and came back to New Zealand about 15, 16 years ago to apply CFD to all sorts of different industries. Sort of, so that's a brief intro of me. CFD, if you're not familiar, it's the main approach used is you sort of get your domain and you slice it up into a series of volumes. And each volume has a property sort of that sort of describes the flow. So you can have the velocity and the pressure and the turbulence throughout the domain, and then you sort of define your boundary conditions and then solve equations across it to sort of end up with the flow field and describe how the flow behaves through the domain, and you sort of iterate away till you get to the final solution. Now, a typical model can have like between 20,000 and 20 million cells, depending how complex it is and what sort of physics you want to capture. And you can apply CFD to an amazingly wide variety of applications. So just basic fluid flow past an object to calculate the drag, or you've got air-water interface and sloshing flow through a pipe, say, or wave loading on large platforms. You can calculate the separation efficiency of cyclones. And you can even do combustion and chemical reactions and fluidized sort of granular materials. So CFD has pretty broad range of capabilities these days. Just to bring it a bit more relevant to what we're talking about today, this is just an example of how you could apply it to sort of breaking waves and loading on seawalls. So there's this example. Oh, sorry. Probably quite familiar, people are familiar with this video, but it sort of captures a lot of the physics quite well. I'm not sure that's playing. Yeah. So obviously a lot going on, and from a CFD point of view, quite a number of these processes can be modeled. It really depends on what the objective of the analysis is. So we just have that mental picture. We just skip along to the next one. So in this example, I suppose there's lots of things going on. There's the hydrodynamics of the water moving, then there's the free surface, the boundary between the water and the air. And as these waves break against the obstacles, water droplets are formed. And I suppose one of the key things is what's that pressure load, what are the impact forces on the sea wall that might exist. The CFD can also model the sand movement along the sea floor. You can model floating objects and how they move. And you can model the droplets as they're formed and getting carried into surrounding area, and the wind and how that affects the waves. So you can do lots of different things with CFD, but really it's a case of defining what the actual objective is that you want to do, and then just model all the relevant physics and don't get carried away, just to keep it realistic. So as far as sea defences go, I suppose that often, this is not my area of expertise, but seawalls can be used to either reflect a lot of the energy in the water back out to sea. But I suppose one of the risks of all of this is pretty high loads can be applied to them. So to design them properly, you really want to know what that load is and how efficient they are at actually projecting the water back. So they're the objectives in this example. And how you'd model it with CFD. So you simplify it down to a two-phase system with just air and water, and looking at the interface between it. Probably ignore the sand and all those other extra bits and pieces. Just adds to the complexity. And with the I use ANSYS Fluent, it's very good general purpose CFD code, and the wave modeling within that is pretty well developed. So you can define waves in lots of different ways: shallow intermediate waves or short gravity waves, and lots of ways, different ways to define those waves. So you can have first order or second, third order Stokes waves defined, and you can define a number of different waves at different lengths at the same time, so it can be overlapping. And there's, in addition to that, you can have sort of wave spectrums, so sort of fully developed sea states can be defined. You just need to define what the frequencies and significant wave heights are and that sort of thing. A key part of any CFD analysis is to sort of provide some sort of validation that the modeling approach you're using is actually realistic. So it's normally a case of going back to a good published sort of experimental data or something measured, and then model that physical sense in with the CFD, and making sure you can replicate the numbers. So in this case, it was just a simple wave run up against a vertical wall, and they had analytical numbers and they had the CFD numbers, and they gave a really close correlation. So it's always a good step to start off with. There's a video just before this. Here we are. So this is a simulation that's simplified down to a two-dimensional case, just so that it assumes the wave is coming perpendicular to the sea wall. So it's two phases, air and water. And as the simulation runs, the CFD refines the grid at the interface between the air and the water. So it's coloured by velocity. And the purpley coloured there is the sort of the whitewash, the air water, which is kind of doesn't represent a pure water. It's a bit dispersed. You can see how the wave comes in, interacts with the wave going out, and then sort of hits the wall to give a load on the side there. So from that, the number of cells required for that simulation is about 200,000. So it starts off a lot less. Then as the simulation progresses, you refine those cells at the interface to sort of capture what's going on. And that takes between about an hour to run 30 seconds of simulation. But it depends on how much computing resources you want to apply to it. It's sort of a typical time scale. So the results give a force per linear meter of wall, and you can sort of see as the waves come in, there's sort of quite a repeatable profile there of the impulse of that initial high velocity wave hitting, and then sort of the bulk of the volume coming behind it. So you have an impulse and a sustained load over time. And if the waves were higher or the tide level was higher, the red was the vertical component, which didn't register in this scenario. You could run multiple simulations, different wave heights and sea levels and things. So that's just a quick intro, like where CFD could be applied. It's very general purpose sort of software, so you can add and take away different types of physics, and really it's a matter of homing in on what the objectives are and what you want to get out of it. So yeah, that's sort of short and sweet, just how CFD could be used. Back to you, Ryan.
Thank you very much, Curtis. Just a bit of a reminder, if you have any questions, please put them down in the Q&A box, and we'll address them now. So just as a start, thank you very much to both of you. I think those are very interesting and insightful presentations. Hopefully we can start looking forward to implementing them in projects going forward. There is a initial question for Richard, who is preparing or publishing the NNBF guidelines.
Yeah, thanks for that question. That sort of dropped off my list. It's led by three main institutions: the US Army Corps of Engineers, the Rijkswaterstaat from the Netherlands, that's the Infrastructure and Rivers Group, and the Environment Agency in the United Kingdom. But there were 77 other public, private, non-government, non-profit and academic organisations, and about 180 practitioners involved. So it was quite a big effort, and it's been going since 2016. So it's had a long gestation time, but it's I've got a near final draft I'm looking at now, so hopefully soon. And Shari, you've had that question on the longevity of some New Zealand examples with things like sea level rise, and I think that's yeah, the longevity kind of issue is something that you do need to understand. The beach nourishment, and one of my first projects that I did as for my university thesis for Mission Bay in Auckland, that's been there maintenance free in terms of they haven't added any additional sand to it since 96. It's working out the right setting for nature-based solutions, and even the salt marsh habitat that we had at Carnoustie. We're currently going through another project using that kind of protected edge planting, and the adaptive response is another layer of rock on the seaward edge to raise the crest levels to manage. So still a lower cost and less volume of material used while creating that buffer. But yeah, so both of those solutions have been around sort of since the mid-90s and are still operating well, but that they have the ability to be augmented with sand beaches and sea level rise, or if you move to cobble beaches, some of that material does get moved landward with wave asymmetry, so that's something that can happen, although in harbour areas it tends to just flatten out, so it's a question of the ability to top up. Or certainly my view is any of beach nourishment in sort of harbour environments need to be done in conjunction with trying to improve stormwater quality and improve shellfish life and biodiversity, because if you can improve water quality and restore some of the loss of habitat for the shellfish, that's a longer term solution to providing sediment to the beach naturally.
Thank you very much. I think there's also another question there for you, which is, are there one or two policies or concepts from the NZCPS that should be kept in the RMA reforms to support the NNB?
Yes. If you like, that cascading selection of options of using enhancing natural systems and using soft engineering approaches before moving to hard engineering, I think is a good thing that to be retained. The challenge of the RMA is when things like a void get taken as an absolute, and avoiding effects is difficult when you're doing a nature-based solution because it does tend to occupy some space in the CMA. So that's a challenge with the current RMA, and I don't think it's the RMA itself, I think it's the application of those policies. But the NZCPS does actually frame things up very well, and when I was working with the US Army Corps, Todd, he came over here and he looked at our policies and rules, and he was pretty impressed that they were quite forward-looking and very aligned with the NNBF kind of approach.
Curtis, there's one question for you here from the Bay of Plenty Regional Council, I assume. Can you export as output wave forces on the seawall with CFD?
Yes, yeah, you can. You can export either the net force over time, or you can do the pressure profile, which you could export to FEA if you want to do some more detailed sort of structural analysis on the wall. So both of those can just be exported in lots of different formats.
And I assume you can get that in any direction you want.
Yeah, it's a matter of defining what surface you're interested in, and just defining that at the beginning. Then you run the simulation, and it just, as it progresses over time, it just keeps exporting those values.
And the council also asked, could the CFD be used to model tsunami impacts on structures at a small scale?
Yes, yeah. There's no limitations there. I suppose the only real limitation CFD is the time scale, really, how long you want to run the simulation for. So waves aren't too long in that sense, so you can run.
I think it's also understanding
quite easily.
any dynamic process of shoreline change or erosion and how that impacts. So CFDs are great, but they're going to be for the defined profile or a range of defined profiles to see that variation.
Exactly, yeah. That's the challenge. Yeah. That's where you need the expert knowledge to make sure the setup of the simulation's realistic and representative.
Pamela's asked, considering CFD modeling is much cheaper than physical modeling, can CFD modeling replace physical models entirely?
I wouldn't say entirely. I suppose it's always good to do that validation step. So that's always best come from a physical model where it's if things are nicely defined and the inputs are quite easily quantified, and then you can model a simplified physical model quite easily, and then you can go and run away and apply that to more complex, larger scale simulations that you could never do with physical modeling. So there's still a place for both, I think.
And Ahmad has asked, Curtis has used kind of adaptive mesh refinement for a simulation presented. If so, is there any comments on when to decide to use that? And if the mesh he uses is 100% error-free in terms of non-orthogonally and skewness, or is it still possible to run with 96 or 97% to get good results?
Good CFD questions there. So the mesh refinement, it's just a matter of running an efficient simulation. So if you start with a nice coarse mesh, there's no need to have a very fine mesh where there's just pure air. So it's just a good way to get efficient running of the simulation, really. And as it progresses, it refines and then coarsens the mesh, depending on the gradient of the volume fraction of water. So it's quite dynamic in that sense. And the CFD code looks after the cell quality as it does that. So you start with a very good quality mesh. You don't deviate away from that. And yeah, it's all well managed. Another question there is
about
can you model
the CFD model?
Yeah.
I don't know if you've got any idea there.
So you can model sand. A lot of my simulations are modeling granular flows, but in an industrial sense. So you could define a beach, and you could define sand as a third phase. So you'd have air, water, and sand, and it would give you insight into how the sand moves, and it's dragged around by the water. But the challenge is the timescale. So CFD you could run for a minute or 2 or 3, but obviously, beaches change over a very long timescales. So you probably look for a different modeling tool for longer scale, but CFD will give you insight in short timescales.
I guess the question is when to go for the more complex CFD model as opposed to something that is more purpose-built. Richard, I don't know if you've got any comments on that one.
I think the sort of discussion of using the right model for the right outcome that you're looking for is pretty important. So what's the thing? All models are wrong, but some are useful. For me, if you're looking at something complex and you're looking at forces, and for design, the CFD is really good at providing information that is very difficult to get out of any other kind of modelling system, even physical modelling. For absolute forces, but it's that short time period, or the short runtime, or the computing requirement you need. But in terms of beach response, there still isn't a good understanding of how waves and currents move grain particles. It's still an empirical relationship with a coefficient. So spending a very sophisticated model to effectively run a clunky sand transport formula maybe not the smartest thing to do, and there's other tools that do that quite well. But if you're wanting forces on a complex structure, and that nearshore or deep water one, that's the thing to use.
If there are no other questions coming up, I had a question, Richard. I was wondering about with using the natural-based implementations, there's a lot of unknowns, and you mentioned that sometimes the outcome may not be what you expected at the beginning. How do you go about using all of the unknowns that you have doing working with nature to evaluate your outcome? As you say, there might be a better outcome in the future, but you can't quite predict the outcome right at the beginning.
Yeah, so I guess it's important to understand the context as well as you can, and identify the limitations, the uncertainties, to see how best you can define them or approximate them. So that like any start of a project, it's getting the data, getting an understanding of the processes that are going on, looking for criticality, what is more or less critical with the objectives that you're trying to achieve. If there was something really quite critical that you couldn't define well, or you had low confidence, I would suggest that's a sign for maybe not progressing with that kind of option, or getting more information so you can improve your confidence. If it's a low criticality outcome, and the confidence isn't high, that you may be able to progress a project, but develop some monitoring around it just to test. So yeah, understanding criticality is important, understanding the potential responses and the confidence of your boundary conditions are all pretty important.
There are plenty. Regional councils also asked if NNBF maintenance costs are more than traditional protection solutions.
Yes. So if we're doing sure, it's possibly more expensive, potentially more labour intensive, but it's also possibly more able to be done by community and volunteers. So if you're looking at planting and replanting regimes, that's something that does require more on-the-ground effort, but it's something that you can do with community groups or interest groups. It's very hard to get the communities with a crowbar upgrading a seawall. The thing with, or my observation, I guess, for structural maintenance is it is often the case that you don't notice the problem till you get catastrophic failure, whereas with NNBF the failures tend to be more progressive and able to be maintained. So there's, I think generally there is a higher cost, or at least a higher monitoring requirement with NNBF, but there are also increasingly better tools, drones, equipping communities with the ability to monitor that can help that.
Steve's elaborated on his question and asked about possibly using CFD for short-term effects of beach profile change, such as scour. Richard, I don't know if you've got any further comment on that for the short term rather than long term effects.
With the limitation of we still have a very poor relationship or a method of assessing sediment transport resulting from waves. I think it's possible to do with granular materials. You probably wouldn't, you'd struggle to do that with cohesive. So it depends on the setting. It would be, well, I'm interested in the expert feedback rather than my response. And I think it could help get you some way, but you'd have to understand what the limitations are.
Curtis, anything further on that?
On the CFD front. Yeah, so on the CFD, modelling granular flows, it's very well established within the CFD code. So you certainly could model how it's dragged and moved around quite easily. It's just making sure the water side of things is modelled accurately. So as long as your waves and currents are well defined, yes, you can model how the sand's moved, and you can sort of give flow rates and things. Lots of values you can pull out of it. So it's just a matter of getting those values that you can extract from the CFD, relate them back to the real world, quantified numbers.
Very true. I see we got 3.5 minutes left. Richard, I don't know if you have any final comments?
No, well, just to say I was hoping to have expanded a little bit more on the guidelines, but have an embargoed copy, so I can't. But I will put it up on the Coastal Society website and happy to talk about it once it's more out there.
Possibly a future, another webinar coming up. Watch the space. Curtis, how about you? Any final comments?
Not really. I suppose CFD is very flexible, so if people have any specific application they're curious about, just give it, I'm happy to.
I'm curious, and I don't want to put you on the spot, but what is sort of the cost order for, say, that seawall wave force kind of thing, so scale-wise, broadly speaking?
Sure. It's very quick to do, so it's $1,000 or $2 maybe, sort of a day's work. They run very quickly, so 20 minutes and half an hour to run a case. So if you get the assumptions right and simplify it down.
It sounds good for optioneering then even. So I mean, looking at different configurations could be really good.
Yeah, and worst case scenarios and test it all sorts of ways.
Cool. Well, if that's that, then I think we'll close off the webinar here. Thank you everyone for joining us, and especially thank you for Richard and Curtis for presenting. I think that was a brilliant, insightful presentation on both fronts, and I think we got a lot out of it. Any other questions, don't hesitate to email them through and we can pass them on to the relevant persons.
Thank you.
Thank you very much.
Thanks, Ryan. Thanks, Richard.
Cheerio.
Have a good day.
Cheers.
Yeah.
Thanks, Holly.